Hello, welcome. We continue our optical waveguides theory and design. We have been discussing so far slab waveguides and what are the guided mode solutions, different approach. First we discussed the ray optics model, and we understand there is a limitation up to certain extent it is useful. Beyond that we need to go for solve the full vectorial wave equations, and in the last lectures we have established the full vectorial wave equations starting from Maxwell's equations in homogeneous medium, particularly in 3-layer structure for 1D waveguide, particularly considering silicon on insulator substrate. This is the reference frame we consider, this is a z axis, and this is so called device layer with having refractive index ND and cladding refractive index NC, and substrate which is specifically for silicon on insulator. It is a box material having refractive index NS such that ND greater than NS greater than NC at lambda equal to 1550 nanometer. Their values are given here. Just for keeping in mind, I just keep it stagnated in the corner of the screen. All right. So, the region for the device layer is one dimensional between x equal to 0 to h and semi infinitely extended this direction, x greater than h and x less than 0, and in the y direction it is also assumed infinitely extended, and no electric field change, everything we are considering in that certain direction. That means also I am considering that any wave is propagating, that is only kz component, this direction propagation vector is there, and any mode solutions supposed to become, that will be because of the standing wave in this direction. So, in this direction there will be some standing wave, x direction some kind of confinement will be there. And as I mentioned that we are focusing only on TE polarization, where only UI component will be there, that is the tangential component, which is easier to handle UI for TE polarization in the interfaces. It should be continuous, here, and we have also we have defined also the homogeneous equation in 3 different media. It is a cladding region we are defining with kappa C. Kappa C is defined like this. Assume that n effective is the propagation constant, effective refractive index of the guided mode, that is the propagation constant related to beta is this one, and obviously n effective will be less than ND and NS greater than NS. Obviously, if it is greater than NS, it should be greater than NC. Okay. And as I mentioned, this whenever you are moving from top cladding to inside device layer, the kappa D will become kappa D square, where kappa D is defined like this, and in the lower cladding kappa S, so this is defined by this. So, considering n effective this condition, this kappa C square, kappa D square, kappa S square all are positive values, because n effective is greater than NS, n effective is lower than ND, n effective is greater than NC. So, that is why all these are positive, and their corresponding solutions we have just considered like this. In the top cladding covering region and standing wave in the core medium within this range, and again it is exponentially decaying in the region where x less than 0. And we mentioned that these are basically unknowns, n effective, phi s, EC, n effective, or sometimes you can say that beta values. Beta values are beta is equal to say 2 pi by lambda by n effective, or this is omega by c n effective. And EC, we have considered EC here, we have considered ED here, we have considered ES here, just a constant, and along with that we have phi s. So, all these things we unknown to us, we need to understand, we need to know how to evaluate them. Then I can say that what would be the modal picture, how they are confined, how the field distribution along x direction for EY. Okay. EY is important for electric field, only component for TE polarization. And since it is exponentially kappa is positive, the solutions coming like that, it will be exponential decaying like this direction or this direction field strength, that is why it is called evanescent field. So, no energy will be flowing, no energy flow in this direction, no energy flow in this direction, no energy flow in this direction, but energy can propagate in this direction, travel as a travelling wave, and which is actually defined by e to the power j omega t minus beta z. Beta is the actual figure of merit actual value actually corresponding to different modes. We will be discussing that in course of time. So far so good. So what we do, we have the solution, this one, this is valid from x greater than equal to 0 to x less than equal to h. That means this is valid obviously at x equal to 0, and this is x less than or equal to 0. So this is also valid at x equal to 0. That means if I put x equal to 0 here and x equal to 0 here, whatever the value comes, they must be equal. So this is at x equal to 0. From this expression what we get? We get x 0, it is actually cosine E d cosine phi s, and here x equal to 0, it is actually E s. So this thing must be 0, must be equal, that is what I have written here. Okay. So similarly, if I go to the other interface, if I put these solutions here, x equal to h, whatever value will be there, I am putting x equal to h, then the exponential term h minus h 0, so it is E c. And from here if I just put x equal to h, that is device layer thickness, so E y E d cos k d h minus phi s. They must be equal at x equal to 0, they are continuous tangential component, we are talking only E y component. No? So that is the reason they must be equal again. So I get another equation in the interface. So that means this thing help us to get some relationship between E c and E d here we could find, and here also we can find E s E d. So suppose if I know the value of E d, so we can consider E d may be here, whatever considering may be normalized to 1, then I can find out E s and I can find out E c, provided if I know what is the value of kappa d and what is the value of phi s. Okay. So now next thing is that E c, E d and E s, they are immaterial, they can be found from these equations obviously, but next thing is that kappa d and phi s, and kappa d and phi s is how to find that. So you need to derive one more equations, okay, couple more equations, so that not one more, couple more equations you need to solve kappa d phi s. Of course we need to know not only kappa d phi s, you need to know also kappa c, kappa s square, all they will be known once you know the n effective. That is you should keep in mind, effective index solution. Any solutions, any guided mode solution if you want, it should have a real feasible solution along z direction, that is related to beta, and beta is related to n effective, that must be known to you in advance. So I have just written those two equations, this equation I have written here and this equation I have written here, for I just stock it for future, and we are just keeping in mind that these are unknowns, though we know that E c, E d, E s somewhat related through this equation, but in spite of that we should keep in mind they are unknowns, I have just written. Okay. Now next thing is that, okay, we just put down here to clear up some space here. Okay. So these two equations at the boundary whatever coming, I have just repeated here, and then we just follow Maxwell's equation now, because we have the solutions for E y and E y, all three region I know the field distribution, electric field distribution, but we have some other components H x, H z. Let us try to see those concentrate on those components, and if we can find some more equations, so that they may help us to find all these unknown constant values. So we start from this Carl equation for the electric field in frequency domain, Fourier domain, Carl E equal to minus j omega, that is basically Carl E equal to minus del b del t, that expression, del t equal to j omega, b equal to mu 0 h, that is what is written. Now we know for this 1D waveguide structure, we know del del y equal to 0, that means along y direction field is not changing, this is the assumption, and del del z, if you just consider only z dependency to the power minus j beta z is there. So, if you do derivative, the partial derivative with respect to z, that minus j beta and same thing will be coming, right. So, we know this thing. Next thing what we know, this curl of a vector we can expand in this matrix form, determinant form. So, this is your unit vector along x direction, unit vector along y direction, unit vector along z direction, and then del del x and del del z, del del y equal to 0 I put here, and del del z minus z beta. So, basically in principle you should be writing like this curl a x, a y and a z, and it should be del del x, del del y, del del z, and then it should be e x, e y, e z. That is actually, if it is vector is e, if it is a vector, suppose curl of a you want to find out what is that thing, then I would be writing a x, a y, a z. So, it is e vector, that is why I have written, and del del y equal to 0 for our waveguide reference, and del del z equal to minus j beta, because of the consideration that okay, mode is confined along x direction propagating along z direction. So, y direction can be 0. So, del del 0, this thing we written. And right hand side if you see j omega mu 0, then I can consider H field as is having x component, y component, z component, though we have defined earlier that this y component won't be there, that is not required at all, but once we consider Ey component and no other components is there for electric field, we will automatically find this Hy is 0. So, that is what we will be getting next thing. So, Hyx is 0 typically, but what about Hx? Hx, because I want to find out this is Hx, this is Hz. So, this side I will find out what is the x component and x component, if two vectors are identical, left hand side and right hand side. So, individual components must be equal. So, Hx obviously that should be also x dependent variations, confinement will be there. I can say that a x component will be this one, you have to multiply this one and you have to subtract by this one. Okay. So, this one means you have j beta E y x equal to j omega 0 h x, x component you equate, and then you get this relationship. So, that means if I say, if I know E y, somehow E y x is known, that expression we have derived earlier. So, that expression is actually directly related to magnetic field x component, only some scaling factor will be there, beta, whatever beta value comes, we are this is unknown though, beta is related to an effective like that, unknown though, but once beta known, but we can say that it is a kind of beta is fixed for a certain mode, that means for that mode E y and h x they are just scaled up, there is proportional, only negative sign is there, that is it, no other difference. And similarly from this expression I can find out z component left hand side, z component right hand side. If I equate, then z component of the magnetic field, I can say that, you see z component means this thing, I am just considering z, these two things barring, then that means this to this and this to this, that means del del x E y. So, if you del del x E y if you do, and along with that you have j omega mu 0 this side. Okay. So, that means j by omega mu 0. So, I can relate. So, basically if you know E y x, y component of the electric field if you know, z component of the magnetic field you can find out by making a derivative and with some scaling j by omega mu 0. So, that is the relationship we are getting from simply from Curl equations here. So, and here also if you see y component, simply if you see y component this one and this one barring, that means this multiplied by this one 0 minus this by this 0 also. So, obviously H y equal to 0, that is clear. So, I can have, if I know E y component, obviously I have derived for x greater than h, within h, less than 0, then if I just make a derivative with respect to x, then I can get magnetic field for the z component, and if it is just multiplying this one, I will be getting y component. So, that means if I concentrate only on EY component, the other component magnetic fields they can be derived using just standard this way. And obviously, you know all these things once you find say Hx and Hz also you will be there, that is also function of x, that will be also function of x. Once you make a derivative, they will be also oscillating with e to the power j omega t, because that is common to both electric field and magnetic field. So, electric field and magnetic field, this part is common. That does not mean that electric field and magnetic field need to be in phase, because we can always consider these fields, these solutions Eyx, whatever it is considered real, they can be complex also. So, their solutions can be complex, so they can be going out of phase or not, that we will see. For the moment, it is as of now it is looking like a same. Okay. Anyway, you see this imaginary part is coming. That means electric field, whatever the thing is there here, y component, x component, they don't have, they are in phase. But if you just consider this one, if you take a derivative also, if depending on this function and j everything, it will see what is their phase relationship, etc. That would be set. Okay. So, we know one more thing, that okay, if you solve for Ey, other components can be easily found using Maxwell's equations. So, I have written down that thing, that Hx and Hz. Okay. Now, you see I just tried to find out what is the Hz component in 3 zones, x greater than h, that means in this region, x within h, x less than 0. Only Hz I am focusing. Why Hz? Because out of 2 components of the magnetic field, x component and z component, Hz component, that means it is oscillating along z, magnetic field oscillating along z direction, that means along propagation direction. So, that propagation direction means that is actually tangential to the interface. So, this is the z component, Hz component will be oscillating this direction. So, this is a tangential to the interface, both the interface, that is tangential. So, you know tangential components are continuous at the interface. So, instead of considering x component, I focus on z component of the magnetic field, so that at the boundary continuity application I can apply. Okay. So, that is why I just derived directly what is the, I have just found directly what is the tangential component or longitudinal component of the magnetic field. Obviously, for x component it is just a proportional, you do not need to make any derivative or etc., because longitudinal component you need to make some derivative. So, if you make a derivative here, this one it is coming minus kc will be there, j omega naught is there, this relationship, along with that minus kc kappa c will be there, that is written. So, similarly, within the core region, that is the equation, and this is the lower cladding region, this is the equations. Okay, straightforward, it is just coming from Maxwell's equations. Okay, I have written down that, this thing I have written down. Okay, good. So, I have now all the components in our hand, that means Ey component, they are in 3 region, and their magnitude, how they are related, that one equation, this equation also known, Ec how it is related to Ed, and Es how it is related to Ed. Okay. And also magnetic field, tangential component of the magnetic field, and normal component of the magnetic field, Hx component, this direction also is known, but I am focusing more on tangential component here. So, I have written down here, all this just duplicated here, and then I try to apply continuity at x equal to 0, because tangential component x equal to 0. I can write x equal to 0 if I put here, this side will become kappa d Ed sin phi s times this one, and this side will be j by omega mu naught. Okay, because x equal to 0 if you put, this is sin minus phi s, minus sign will come, minus plus, and here also plus is there, x equal to 0 you get something. So, you get a 0 if you just equate this thing at x equal to 0, put x equal to 0 and equate these 2 equation, then you will get this one. Okay. That means, I have a relationship, one more relationship apart from this one boundary condition here, I have one more equation here. Similarly, I have boundary at x equal to h, I have one more equation here. I just put x equal to h here, x equal to h here, and then I equate. So, here kappa d Ed and here kappa c Ec, they are how related through this one. So, I have 2 more equations, equation number 1, equation number 2, equation number 3, equation number 4. Okay, fine. So, I have written down this equation, we have written 4 equations. So, our unknowns are this one, I should keep in mind. My ultimate goal is that to find out all these values. How to find that? Let us move on. So, only keeping this thing. Okay. Now, you relate these two. Okay. Just I have ignored, I have removed the magnetic field, because whatever necessary equations I have there. So, I am again concentrating only on electric field, and this equation and this equation, if you just compare, just divide it, then what you can eliminate? You can eliminate ED, you can eliminate ED, you can eliminate EC. Okay. Then that means I can have a relationship between phi s and Kc Kd, kappa C kappa D, phi s kappa C kappa D, kappa C kappa D, what is both cases n effective unknown, here also n effective unknown. That means in this equation I have 2 unknowns. So, if I want to solve n effective and phi s, n effective kappa D also phi n effective, right. So, in 2 unknowns are phi s and n effective unknown. So, relating this thing, one equation I am getting, and another thing, if I relate these 2 equation, I get another equation. Okay. So, again I have 2 unknowns, n effective in this 2 equation, n effective and phi s, n effective and phi s. So, I have 2 equations, equation number 1, equation number 2, 2 unknowns. So, it would be easier for us now to solve that 2 unknowns, 2 equations, you can just solve. Since they are not so easy, just to eliminate one and to get one solutions, Gaussian elimination method, so that is not so easy. So, we little bit move in little bit tricky way. So, I have written down these 2 equations like this to get some space this side. Okay. So, you assume this kappa C kappa D, because you know kappa S by kappa D you are getting tan phi S. So, kappa S means this one, and kappa D, their ratio square root, that is actually tan phi s. So, again kappa C that is related to your top cladding, cover cladding. Okay. So, there also I can just define one more parameter, introduce one more constant phi C, intentionally put phi C. That means one more constant I have introduced, that will help us actually, because kappa C kappa D known, that means I know phi C. So, once an effective known, I can find phi C. So, effectively this constant is not additional thing, it is all inclusive. Okay. So, now what we get? This equation we get kappa D H minus phi S, and right hand side phi C, because if I compare these two. So, this I am replacing here tan phi. So, I can write kappa D H minus phi S equal to m pi plus phi C, because you know tan function, it is periodic over pi. Okay. So, that is the reason we can easily write this one. I am now getting a generic equation where m equal to 0, 1, 2, 3, 4, 7. So, this equation is true for this thing. So, every pi it will be repeating. So, I am just now similar to our ray optics model, I could introduce one more integer here also similar to that, that is m. So, that means if I try to solve this, one particular 0 entry will give me one set of solutions, another set of m equal to 1, I will get another set of constant solutions, m equal to 2, another set of constant solutions. So, it is something similar to whatever we solved earlier in ray optics model, theta naught, theta 1, theta 2, and so on, effective m there. So, here also almost similar results we are getting. Okay. So, from this one I am just simply manipulating left hand side, right hand side. So, you are getting same way left hand side, right hand side. Here also I have n effective here, function of n effective. This one also will be function of n effective. This one also function of n effective. Both side is a function of n effective. I have completely eliminated the constant EC, ED, EC, ED, ES. All these are not there. I have just equation, a single equation, which is only n effective involved. Okay, nothing else. So, that means phi s, tan phi s also this is similar to phi c, this is also only, if you check clearly, this is n effective involved. So, kappa s by kappa d, all are n effective, all other things are known, omega, c, nd, nc, ns, everything known. So, I have the transcendental equation here, and that is some kind of eigen solutions we can consider for guided mode. Okay. So, this thing I am just simply writing kappa d h equal to m pi phi c equal to tan inverse kappa c kappa d and phi s equal to this one. This is so called transcendental equation. Left hand side and right hand side both are actually ineffective there. So, we can similar to ray optics model, we can just plot left hand side as a function of ineffective. I can plot left hand side as a function of ineffective some value. Ineffective can range from ns to nd, and right hand side also I can plot as a function of ineffective. So, I will be getting, say somewhere I will be getting some intersection, and that intersection will be solution for the ineffective. Discrete solutions you will be getting for different m values. So, instead of solving theta and then ineffective, we have the equation now directly we can solve ineffective instead of theta. Okay. So, then we do not need to, the ultimate goal is that we have shown that the ray optics model, the theta, it is very difficult to control that which particular angle you can go for, you need to couple. Instead I think normally in practice we can couple light for all modes, but ray optics picture it is somehow it is not giving good understanding how you could excite different modes, because theta angle is somewhat Snell's law dominating, controlled by Snell's law, and according to that you cannot control in principle. But here we do not have any theta, we have the only solution for ineffective, and then we can see how coupling is, whatever the coupling is coming from the whenever you are shining light from the output side and trying to launch different modes, and normally practically they are coupling, and how much they will be coupling to different modes, that weightage we should find out in a different way at least. You do not need to bother about theta all this, whether it is in principle it is satisfying or not, those things you do not need to concentrate. Okay, fine. So, next thing is that from this equation you can solve whatever the ineffective m. You just change m value, you give a entry m equal to 0, one value ineffective 0, and you get m equal to 1, you get another solution, and for that everywhere I am just using this thing. For certain value n ineffective will be there, I will be finding first ineffective 0, and then I will be finding ineffective 1 for m equal to 1, and then I will be finding ineffective 2 for this thing I can solve. I know ineffective values I know, then I can find ineffective m, right, ineffective m can be 0, then I can find one kappa c value, m equal to 0, I will be putting in, if I put here 0, I will put there 0, I will be finding an effective 0, that solution if I put, then I will be getting kappa c 0, and if I put m equal to 1, that is means n effective 1 I will be putting lambda known here, whatever the things, all other values are known, NC known, then I will be getting kappa c 1, and then I will be getting kappa c 2 corresponding to n effective. Different solution gives you different value. Likewise you can get for kappa d, likewise you get for kappa s. That means I get a set of kappa values, kappa c, kappa d, kappa m. If 0, I can put one kappa value here, corresponding kappa value here, kappa d, corresponding kappa d here, kappa d here. So, I get a one set of solution. If corresponding to m equal to 0, that is the solution for fundamental mode. Once you are putting 0 here and getting 0 here and 0 here, that means corresponding to m, corresponding to n effective you are putting, whatever the solutions you are getting, and you can use their relationship here also. And phi s, obviously you know phi s value, phi s equal to tan inverse kappa s by kappa d or something like that, kappa s kappa d. So, then you can find whatever the profile, all the three region you know now. So, that is fantastic. Now, you take here, that is the whatever I explained, that if you just enter here all these values, kappa c goes here, kappa d comes here, kappa sm comes here, sorry here, kappa sm comes here, and whatever boundary condition also you are getting, that will be also no more EC, that will be m dependent also, ECM, EDM, I have just introduced that corresponding m equal to 0 means everywhere whatever solutions you are getting, they will have different set of relationship. Okay. So, 3 regions, 3 solutions, and boundary condition actually relates with the EDM to ECM and ESM here. Okay. So, all these things are solved. So, these unknowns is no more unknowns, no, all these are known. Only thing is that if you are putting ED equal to 1, ES I can know from here and EC I can know from here. Okay. And phi s also known, phi s is related to tan phi s equal to whatever the things, tan phi s I mentioned earlier again, tan phi s equal to say kappa s by kappa d, okay, tan phi s. So, once you know phi s, once you know kappa d, once you know ED, then you can actually know what is the field distribution here and what is the field distribution here and what is the field distribution here, and they will be satisfying actually in the boundary continuity also will be satisfied. So, we will be able to plot also this how these fields will be looking like using these equations, and we can derive this equation. So, it is straightforward. So, we do not need to consider any more theta. Okay. Now, so let us see, if I just consider m equal to 0, m equal to 0 everywhere we put, that means I need to solve kappa c 0, I need to solve kappa d 0, I need to solve kappa s 0, and they can be solved because we could solve n effective 0. And once we know n effective 0 and I know this one, this one, this one, and then I can find out what is the value of phi sm. And if I consider EDM equal to 1, so EDM equal to 1 means phi s known, kappa d known, I can find EC and I can find out also ES. Okay. All these values will be known. So, I can actually plot in the core region, this is your core region. You see I am considering h equal to 1 micron, thickness earlier consideration h equal to 1 micron, 1 micrometer. So, I start from 0 here, 0 here. So, this is your device layer ND. So, this is your SOI silicon layer and this is your box layer and this is your top layer, this is for cover layer. So, this is x greater than equal to h, this region h equal to 1 micrometer, here it is shown in nanometer scale and here it is 0 scale, and then this is cosine function, right. If you just plot, use simple MATLAB program, then you can find out that okay, field is coming, and in the interface you see it is not suddenly it is dropping 0 because of the evanescent field. This field you can plot here, they are continuous, and similarly you can continue. So, that means even though effectively your waveguide thickness is h, your field distribution, this is again I am just showing this axis is your field strength, this field strength I am showing, though it is actually if you are considering this cover region, core region, cladding region, this is z axis, this is z axis as well as electric field strength I am also showing. So, everything is positive, this is the field. And whenever you see this is the field distribution x direction, if your x direction waveguide is confined, okay, you want to confine along x direction. So, this would be the field distribution for the fundamental mode, and this distribution is entirely together we will be calling like a EY x for 0 field distribution, and that is EY component, and that will be oscillating along y direction, and that will be propagating along z direction with the phase velocity like this beta 0 z. So, this will be your E0 E0 x z t along y direction I am not considering anything. Okay. So, x z t, that is actually this is the field, electric field associated to the fundamental mode, and you know once you know all this field, you have already solution for magnetic field also. You can find out for T polarization, we are considering T polarization, you have to consider EY field and HX field, HZ field, and we know from the Maxwell-Scarl equation how they are related. So, you can also plot how the distribution for HX and HZ, they will be also x dependent distribution will be there, associated with that they will be propagating in this direction. So, that means whatever components you derive, okay, that is a field component along x direction, what is the profile, and you know which direction they will be oscillating, and you know all of them will be travelling along the z direction like a mode. So, particular mode is a particular pattern of electric field, particular pattern of magnetic field, and they will be traveling with phase velocity. So called phase velocity will be omega by beta naught. That will be actually I can consider Vp0. That means fundamental mode, what would be the phase velocity? Beta naught will be 2 pi by lambda times n effective 0, fundamental mode effective index. Okay, good. So similarly, I can also consider for the m equal to 1. If mode m equal to 1, then you can calculate what is the kappa C 1, because kappa C 1 again you get from n effective 1. You have the value of n effective 1, use that n effective 1, n effective 1 will be this one for m equal to 1, that value also given here for h equal to 1 micron. Okay. So once you know n effective 1, you can get kappa C 1, you can get kappa D 1, you can get kappa here kappa S 1. Once you know kappa S 1, kappa C 1, kappa n, then you can find E y for the first order mode. That variation will be, you can find this one and this one will be in the core region and this will be in the lower cladding region. So after solving, if you try to plot the electric field as a function of x, you will see this one. This is your mean position, then electric field, this is actually electric field. If you see electric field strength, the first half electric field will be, you see the field direction is this direction. Okay. At any instant of time, if you see field direction, you will see at any instant of time this is something like this. So and then it will also electric field will be this side, that will be negative electric field, that is negative sign, and this will be positive. So this is positive and this will be negative, and slowly as time goes on, e to the power j omega t will be there, right. So this amplitude, if I considering t equal to 0, as t rolls down, so that will be actually reducing, and that will be also reducing at any point if you are considering reducing, and then it will start moving in other direction. So one half to another half, it will be actually, okay. So you will be getting this type of pattern again. So that will be oscillating back and forth with the frequency of optical frequency, the frequency omega, with that frequency that will be oscillating. But all the time you will see that upper half the electric field will be positive and lower half will be electric field negative at any point. This is if it is considering also propagation direction, at any point you are considering like that. So that is how mode distribution. Again this mode, if you see how it is propagating along z direction, then we have to write omega t minus beta 1 z. Beta 1 you have to calculate. Once m equal to 1, beta 1 will be equal to 2 pi by lambda times n effective 1. So once we know that, then we know how the first order mode also that will be propagating. Then for m equal to 3, we have 4 modes. You know, for h equal to 1 micrometer, there will be 4 modes. That 4 mode solutions we could find, okay, and that mode 2 field distributions will be this one again. You are getting like this, that m equal to 2. That means you can again calculate kappa c 2, kappa d 2, kappa s 2. Once you put n effective 2 value in kappa expression, and once you get this one, corresponding values for the ECM, you can find out all the kappa dm phi s, you just put down, and then ECM, that m equal to 1 you can find. Again you can just plot, and in that case also you see electric field, you get one more situation. So you get this is positive electric field, positive direction at any instant of time. If you see, this is positive, and in the middle it is showing negative direction electric field. So that way it will be oscillation, standing wave will be created like this, and next instant you can see that after pi phase shift, after t by 2 time, you will see electric field will be something going like this and going like this and going like this. Okay. So it will be like oscillating standing wave, right. It will be oscillating like this, it will be oscillating like this. Okay. But at any instant of time, if you see, if this is plus, this side, this is plus, the middle side will be minus. If middle side becoming minus plus, then this side will be minus, this minus. So that is again it will be oscillating with the optical frequencies. Okay. That is m equal to 2. Then the last mode, if you see m equal to 3, m equal to 3, same way if you just see, you get one more situations. this will be say for example plus, you can consider this is actually 0 point electric field 0 point. So, at any position at z equal to 0 or something like that. So, because you know that E y you are considering E y x e to the power j omega t minus beta z. You can consider at z equal to 0 and t equal to 0, then only you are plotting this one E y x. So, E y x is this, these are the expressions. These are the expression. If you see that at any instant of time at any position along the propagation direction, you see this is plus, this is plus, this is minus, minus. And as time rolls, this will be oscillating like a standing wave along x direction. Okay. So, you can see something like this. It will be oscillating, energy will be something like this. Yeah. So, this is 3 nodes, anti-nodes you will be seeing that maxima, 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 this will be seen. If you see the intensity pattern, you will see sometimes it will be averaging over time, right. So, you will be getting one spot like this here, and another spot will be here, and then another spot will be here, then another spot. You will be getting 4 spots. So, 4 spots means it is a mode number 4th mode. 4th mode means you are starting from m equal to 0, that is the first mode, m equal to 1 second mode, m equal to 2 third mode, m equal to 3 4th mode. So, 4th mode means vertical direction along x direction. If you see the intensity, you will get 4 spot. Similarly, if you just check here, you would be seeing 1 spot, second spot, third spot, standing wave pattern, and node anti-node you will be seeing like that, right, standing like a standing wave pattern along the vertical direction. Okay. So, 3 spot and you can see the 4th spot, right. So, with this I just stop here for today's lecture. Now, we know how to find out field distribution, and what once you know beta and you know what is the phase velocity also, okay, and you can normalize to 1 if it is EDM is, suppose this mode is carrying certain field amplitude, say volt per meter or something, amplitude electric field, no, volt per meter. So, you can consider 1 volt per meter. If it is 5 volt per meter, then you have to multiply 5 times this one, this amplitude will go 5 times. If it is 10 volt per meter, then it will be 10 times. Okay. Now, I am considering 1, this is a normalized value and all other parameters known to me. So, I know now. Then I can find out, this is of course calculated for h equal to 1 micrometer and at 1550 nanometer. All of them they are lambda dependent or omega dependent, right, and h dependent. H is always there, everywhere h is there. So, h value, depending on h value, depending on the lambda value, depending on the refractive indices, etc., you can find how many solutions, how many modes will be supported, and what would be their phase velocity, almost all the information known, right. So, now we will be discussing next that okay, all the information known, what about the modal dispersion, whether this effective index, if it is calculated for lambda at 1550 nanometer, the same effective index will be there for other wavelengths or not. That I will be discussing, the dispersion basically. I will be trying to find out whether this beta value is a function of omega or not. I have calculated for lambda or particular omega. So, if you are changing omega value for same waveguide, same 1 micrometer thickness, then how it will be propagating, what would be the relationship, because that is actually very, very important to understand how device will be working for a complicated circuit, in a complex circuit. With this, I just stop today for this class. Thank you.